System 1. ATP-PC system. What's the timeline for ATP-PC?
5 plus 10. 10. And 15.
A little bit more, 15 to 20. All right. System 2, glycolysis. So from around 25 to about 2 minutes. Good. And on Friday, we were looking at adaptations if we are training events that are predominantly glycolytic, then I think we have been through, we looked at, oh,
that would help the next batteries were in the right way around.
all right, so we looked at one adaptation that was an increase in the enzyme activity. So for that 10-step process, there's a specific enzyme for every step, every different breakdown of the substrate. Okay. So we see a change in enzyme activity, and we also see some increase in the level and the amount of enzyme that's available within the muscle cell. So that means that I can do glycolysis faster, and the faster I can do it, the more ATP I can get. Okay? And then glycolysis breaks down carbohydrate. So again, adaptations are typically positive. Right? So you're always looking for, if I know what's going on, what would be something that would be beneficial to that process, and that's likely to be an adaptation. Not every time, but quite often. That's an easy way to go about it rather than learning another set of material. So if I'm breaking down carbohydrate and I'm training this system, then a good adaptation would be to have more carbohydrate available to the system. Yes? Does that make sense? Yes? Okay. Talk to me, people. See, you have sugar, everyone goes quiet. All right. I hope you didn't eat that on an empty stomach, guys, otherwise your brain is going to be going in about 10 minutes. All right, so the last type of adaptation that we would see is an increase in the cell's ability to buffer the hydrogen ions. So remember, the hydrogen ions are acidic, and the enzymes are very fussy about the range of pH that they're willing to tolerate. So once I start breaking carbohydrate down and releasing hydrogen ions, then I'm starting to change the pH, and that can cause a problem. So the better able I am to balance the hydrogen ions, the longer I can keep going before the acidity builds up. Right? So a buffer is typically an alkaline substance. It's just the opposite end of the scale from an acid. And we want to be able to buffer them for as long as possible so we can go for a little bit longer. And then we want to be able to recover as quickly as possible once we've finished the sprint or whatever it is that we were doing. So by training the system, ignore the endurance bit for a minute, we'll come back to that today. If I'm training the system, so if I'm doing a sprint event that is long enough to get me into predominantly system 2, so not 100 meters, not 200 meters, but once I start looking at, I guess, a 400, 800s, right? Then we're looking at the glycolytic system. So the length of the training program then dictates which system we see the adaptation in. So if I'm doing sprints, or I'm doing interval training, and my sprint element is less than 10 seconds long, the adaptation that I'm going to see will be in system 1. Right? If I'm doing sprints and the sprint element is more than 10 seconds long, then I'm going to see more adaptation in system 2. All right? Making sense? Sure, because we need to go on to system 3. We don't want to get too confused. All right, so system 3 then. Systems 1 and 2 do not use oxygen, therefore they are anaerobic. Right? System 3 has several levels to it, but ultimately we have to have oxygen available in the cell, and so system 3 is an aerobic energy production system. Right? Depending on which textbook or which website you're looking at, they may call it oxidative metabolism because it uses oxygen. So, the first part of the aerobic system is called Krebs cycle. And it is a little bit like glycolysis in that it's got all these ugly terms all the way around, right? Most of which we don't need to know off the top of our heads. Right? That's what textbooks and the internet are for, very useful. I don't want you to waste your time trying to learn every step. Right? But there are some things about Krebs cycle that we have to pay attention to and understand. So if we summarize Krebs cycle, then what I have is a substrate coming in, and that substrate is turned just before the cycle into something called acetyl-CoA. And it's acetyl-CoA that feeds into Krebs cycle. We'll come back to why that's important in a minute. Acetyl-CoA is a 2-carbon molecule. And acetyl-CoA is going to feed in to this breakdown of the substrate called Krebs cycle. And from one molecule of acetyl-CoA, as it gets broken down, we get one ATP. Okay. So, in your head, be thinking what we've got energy-wise so far. Okay, ATP-PC doesn't need a food to feed it. It relies on things that are already sitting in the muscle cell. Okay, but I only have enough sitting there to get to somewhere around 22 seconds or so, depending which book, anywhere from 15 to 22, depending which book you're looking at. Then I have to start using carbohydrate. So I can use carbohydrate predominantly for two up to maybe 3 if I'm training that system and I'm getting lots of carbohydrate in the store. But how many ATPs do I get in glycolysis? What did we say? 3. When do I get 3? Glycogen, right? So if my carbohydrate is glycogen, then I get 3 ATP. And if it's glucose, how many ATP do I get? 2. So, per molecule, so far we're not creating an awful lot of energy. Does that make sense? So, given a molecule of acetyl-CoA, we're still not making very much energy because now we only get 1 ATP. We also get some carbon dioxide. Right, we get carbon dioxide, we get lots of hydrogens. So we're making more acid and we're still not getting very much energy. Now, this is where we have to be paying a little bit of attention, because the thing I can feed in here can be either carbohydrate or fat, and if I absolutely had to, it could be protein. So we take carbohydrate and fats and we turn them into acetyl-CoA, and then we feed it into Krebs cycle. Because the big pink sign didn't say. So, with me so far, right? When we looked at glycolysis, what was the very last molecule we ended up with at the bottom of glycolysis? Pyruvate, okay? So, my carbohydrate is pyruvate. So I have to break glucose or glycogen down in glycolysis, and then if I'm going to work aerobically, I take that pyruvate and I turn it into acetyl-CoA. That's why when you look back over the glycolysis notes, every now and then you see endurance work, which would be aerobic, because even though we don't use aerobic metabolism if we're doing a quick, short event, we can use glycolysis to feed aerobic work. My fats are going to come from another system. When we break down fats, there's a different system that we don't tend to talk very much about, because when we break down a fat, the equivalent of glycolysis for a fat molecule doesn't make any ATP at all. Right? So we don't tend to talk about it when we're looking at energy production, because we use the byproduct and we feed it into this bit, but the first stage doesn't make any ATP. So if we were doing another semester's worth of XPhys, if it was a one-year course, or if this was a graduate class, we would look at fat metabolism. But we don't have the time to spend it, okay? So I can break down protein and end up with acetyl-CoA and feed Krebs system, but we don't do that very often. mostly carbohydrate or fat. Which is why, if I'm trying to lose weight, we say you've got to do some aerobic work. Because if I do anaerobic work, it doesn't utilize stored fat. But if I want to get rid of stored fat, I have to do aerobic work. Because this is the only thing that uses fat as an energy source. Yes? No? Making sense? All right. So we still don't have very much ATP. So we've got to have, there's got to be something else happening. So this is the first step. The second step is called electron transport system or electron transport chain, depending where you're looking. And the electron transport chain is where all the ATP is made. So is everybody okay with this diagram, this idea? If I rub this off. Usually I just keep going along the board, but I'm not sure how the camera will work if I do it. If I keep going, it'll be okay? All right. All right, so electron transport chain. This part of the system occurs in what we call the mitochondria. So system 1 and system 2 occur in the muscle cell, in the sarcoplasm, and then the substrate gets moved into the mitochondria and turned into acetyl-CoA. So the mitochondria, when you were in biology, is the little thing that they always draw that looks like that, right? And it's often called the battery of the cell because it's where most of the ATP is made. So what we do is we steal the hydrogen and we transport it to the electron transport chain. Often the ETS is pictured like a waterfall. So it starts, and the diagrams often look a bit like that. This again is a lot of different chemical reactions, and actually what we do is split off the electron and then we join them all up again at the bottom. But for our purposes, we're going to pretend like we feed in the hydrogen and it just moves through the chain to the bottom. As it moves through the chain, we get tons and tons of ATP given off. Lots of ATP. If you look at page 40, I think it's page 40, double check. Yeah. If you look at, there's a table on page 40 and then there's another one on page 44 which does the same thing for a fact, all right? The one on page 40 is looking at how many ATPs I get from a carbohydrate. And you'll see that at the bottom of the table, I get either 38 or 39. So, depending on whether I fed in glucose or glycogen, because I get one less here. So I've got however many ATPs from glycolysis, then I've got ATPs from Krebs cycle, and then I've got ATPs from electron transport chain. So for one molecule of glucose or glycogen, for a molecule of carbohydrate, if I'm working aerobically, I can get 38 or 39 ATPs. That number changes every now and then, so don't get hung up on the number. When I was in school, it was only 32. I suspect it will go up or down over the next few years. So it's not the exact 38, 39 that I'm interested in. Okay? It's the idea that we're not looking at very much energy from a carbohydrate molecule. That's the key. Right? Overall, we don't get heaps and heaps of energy from carbohydrate, but carbohydrate is very easy to get at because it's a small molecule. So as a very quick source of energy, it's very useful because it doesn't take very long to break it down through this. Okay, so far? Next bit? All right, next bit. How do we get the hydrogen to the electron transport chain? Right, we have a couple of bus systems. And the bus is either NAD, oops, that's a D, or FAD. NAD stands for nicotine adenine dinucleotide maybe, which is why we call it NAD, because the word is too long, right? So NAD and FAD make it much simpler. Okay. Think of it like a red bus or a blue bus. Okay. So they shuttle backwards and forwards here. They pick up the passenger, the hydrogen. They drive over, they drop the hydrogen off at the electron transport chain. Okay. When you look at some of the tables, it gets a little bit complicated because in that 38 or 39 is also which carrier. NAD likes to climb all the way up the hill and drop hydrogen off up here. FAD is a bit of an old bus and it doesn't like to go all the way up the hill, so it drops its hydrogen off partway down. So we don't get quite as much ATP if FAD is the bus that picks up the hydrogen. Either of those can be the bus, either of them can pick up the hydrogen. They're both going to take it to the electron transport, and the hydrogen going through the electron transport generates lots of ATP. Okay. We get to the bottom, and we have hydrogen. What's the problem with hydrogen? It's an acid. So all we did was move our acid problem then from over here to over here. So those of you with the red lights going off are going, well, hang on a minute, we've still got a problem now because acid causes us some difficulties. So we have to get rid of the hydrogen. We've got to make it not acid. Did I mention oxygen yet? What happens when I join oxygen and hydrogen together? I get water, right? This is what makes it aerobic metabolism. Because I have to have oxygen available in the cell to bind with the hydrogen and make water. Water is pH neutral, doesn't cause the muscle or the bloodstream any problems whatsoever. It's easily got rid of out of the body. I urinate, I sweat, and I breathe vapor. Right? If I breathe on a glass, you get water vapor on the glass. Right? So getting rid of water is very, very easy. It's pH neutral, so that means as long as I've got oxygen coming in to pick up these hydrogens, I can keep making ATP because I don't cause any kind of environmental problems. So I can do aerobic work for hours and hours and hours because I never get a build-up of hydrogen ions if I'm working aerobically. To a point, right? I can max out. I can get to the point where I can't get in any more oxygen. I'm doing it as best I can, and yet I'm still making hydrogen. But not very many of us get to that stage. How are we doing? Okay, so how many carbohydrates? Oh God, brain. How many carbons did pyruvate end up with at the end of glycolysis? 3, right? Remember that glucose and glycogen are 6 carbon molecules. We break it in half, halfway down glycolysis, I end up with 2 3 carbon molecules. We said that acetyl-CoA is a 2 carbon molecule. So for every piece of carbohydrate, I get 2 pyruvates. I can only get 2 cycles of acetyl-CoA. I have to drop a carbon as I'm turning it into acetyl-CoA. So for every molecule of carbohydrate, I can only do 1, 2 cycles, because I've got 2 pyruvates to feed in, 1 ATP, and move the hydrogen over here. So, even though I can get a lot more ATP from carbohydrate aerobically, I still can't get a ton of ATP. A fat, on the other hand, the stearic acid that's on that first slide from last week was 18 carbons, and that's the simplest one there is. Right? Fats have loads and loads and loads of carbon. That means when I break a fat down, I get a lot more acetyl-CoA. So I can do a lot more Krebs cycle, I can throw off a ton more hydrogen, and I can make heaps and heaps and heaps of ATP, as long as I've got enough oxygen coming in. So, ETC, ETS, depending on where you're looking, is where the majority of the ATP is coming from. That's why I can keep going aerobically for a long time. And I can't keep going anaerobically for very long. Right? Can't keep it up for very long. So if I'm playing a basketball game or I'm playing a soccer game, we have short, sharp bursts, and then we're jogging or walking. Or in football, we switch out our teams. Right? So I get to go sit down for a little while, right? And then I get to come back in. So when I'm playing soccer's a bit of an oddity, and we'll talk more about that during the semester. But most of soccer is anaerobic, although they don't tend to walk very much in a good soccer game. Right? Most of basketball is anaerobic because you sprint down the court and then you stop. Cycling, swimming, running are aerobic because I keep going long enough. We come back here, system 3 picks up somewhere around, it becomes predominant somewhere around 3 minutes. And it goes for however long you want. And so when you're sitting here, because you're sitting and you're not working very hard, intensity is low, you are working predominantly aerobically while you're sitting in class. You are working predominantly aerobically when you're asleep at night. Does that mean I'm burning heaps and heaps of calories and getting thin? No, because then we have to factor in some other things, right? Because I'm burning fat, but I'm not working very hard, so overall I'm not burning very many calories. If we go back to our seesaw, right, remember the key is how many calories do I use versus how many calories do I eat. How are we doing? Brains okay? No? So, how hard I'm working is a crucial key. Right? The technical term for how hard I'm working is intensity. Pay attention, because intensity is one of the things you have to be talking about in your projects. Right? So you want to make sure that you have a good feel for the idea of intensity. So, if we ignore protein completely, because it makes the picture easier, ignore protein. We'll stick with, we're going to use carbohydrate or fat as an energy source. And so, at rest, when I'm not doing anything, most of my energy is going to come from fat. 66% of the ATP that I make comes from fat. It's just that I'm working at such a low intensity, that work is so easy that that doesn't equal a lot of calories. As I start to work harder, I have to start using more carbohydrate, because the harder I work, the quicker I need ATP, and fat is too big a molecule. So I have to start using a bit more carbohydrate the harder I work, because I need to be able to get at ATP quickly. So we have a continuum from not working very hard, can be a lot of fat use, to working very, 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 very hard would be basically completely carbohydrate use. So, some of the things that make that occur when we look physiologically is that carbohydrate is going to produce more energy per liter of oxygen. So it's not more energy per molecule, but for the amount of oxygen I can get in, I can get at more carbohydrate. It's easier to break down. We haven't talked about muscle type yet, but we will be talking about muscle type very soon. Whether I have very powerful muscles that contract very quickly, or whether I have muscles that contract more slowly, will somewhat determine whether I use carbohydrate or fat. So when you're sitting here, all your postural muscles are quite slow twitch. Right? So they're able to use a lot of oxygen to keep you sitting upright, mostly sitting upright in your chairs. Right? When I run very fast or I jump, I have to create power, which means speed. So I have to contract muscles very, very quickly. Well, that's not good if I'm trying to break down fat, because I can't break down fat quickly. So fast fibers use carbohydrate. So intensity plays a big role in whether or not I'm using fat or carbohydrate. The other thing that plays a big role is duration. How long am I moving for? Right? So, the longer I'm moving, then the more fat I'm going to use. The shorter amount of time I'm moving, the more carbohydrate I'm going to use. So if I jog for 30 minutes, then For most people, somewhere around 20 minutes is when we switch over. So of my 30-minute jog, somewhere around 20 minutes will be carbohydrate as I get going. And then once I'm going for long enough that I've started to break down these great big fat molecules, I can use some fat. So somewhere around 20 minutes. So the last 10 minutes of my jog, I'll be using some fat. If I have a high carb meal, then I'm going to have a lot of carbohydrate in my bloodstream and in my muscles, so I'm going to use a bit more carbs. Or I'm going to have some carbs left over for later on when I need them if I want to sprint into the finish. Because it's all very well, right, jogging around this marathon, but you get within 600 meters or so of the finishing line and you can see all the banners and there's someone sitting right on your shoulder. What are you going to want to do? Beat their butt to the line, right? So I need to be able to sprint. But I've been running for 2.5, 3 hours. But that's okay because it's not the same system. Okay? Running my 2.5, 3 hours uses this system. As long as I don't get rid of all my carbohydrate, when I sprint, I can come back here and sprint into the line. So, something else we'll talk about quite a few times over the semester, and if I forget, yell at me, is carbohydrate loading. If I'm an aerobic athlete and I'm going to be using mostly fat, why would I need to carb load? Because if I want to sprint at the end, I need carbohydrate left to come back to sprint. I can't sprint using fat. I can only sprint using carbs. So, if I don't care about sprinting in at the end of the race, it doesn't matter if I ran out of glycogen. But if I want to be able to kick in at the end, I have to have glycogen available. And that's why carb loading can be really useful for people who are glycolytic athletes or endurance athletes. No good whatsoever for this person. Right? Carb loading is a waste of time if I'm a 100-meter sprinter. Because I can't use carbohydrate anyway, so why would I need more of it? And I store water when I store carbs. And that makes me heavy. So a 100-meter sprinter doesn't want a carb load. Right? Lots of pieces of the pie. And when it's your first time in X-Phys, there's like too much information and it's difficult to try to keep track of it all. So it's really, really important that you go back and look at this again. Wednesday we'll do a little bit more. But you've got to review it in order for the pieces of the pie to kind of start to fit together. They're not going to completely fit together, all right? I know when I was an undergrad, I was sitting there going, okay, I know glycolysis. All right, I know glycolysis, that's great, but I couldn't put glycolysis in the big picture. So what I'm hoping is that by trying to say, don't learn glycolysis step by step, don't learn the circle step by step, that it will give you brain space to try to link the three systems together, because that's more important for you guys as a group. So, what have we got left to cover here? We're going to do, I've got some diagrams for you, and then we'll look at lactate thresholds, and we'll look at aerobic adaptations. Okay. So, let me see. Am I behind on my schedule? Probably. Probably. Too slow. Should go faster, but the eyes weren't going, so I thought I'd slide in. Let me have a look. Oh no, we're all right. Oh, I was smart, I built in 4. Okay, so Wednesday, we will finish off these notes and try to put the picture together. Friday is a review session for exam 1. So Friday we will have an opportunity for you to ask questions for anything you want me to go over again. Monday is exam 1. Already, right? I know it's already, but trust me, you don't want to have to do 4 chapters of study. It's easier to do 2 chapters of study, especially when you got this chapter. All right? Okay.